Welcome to week 4. This week we're going to be continuing our introduction to ordinary differential equations. And remember, ordinary just means that there's only one independent variable. So it's a function of t, it's a function of x, it's not a function of both x and t. As usual, we will start off our video with some review questions. So I'm going to give you the general solutions to differential equations and initial conditions or boundary conditions, and I want you to find the particular solutions. Okay, so here's your first one. This is actually a very common form of a solution that occurs in physics all the time. Okay, so take a moment and solve these to find the particular solutions. And in case this is a little bit hard to read, it says 1/4 times t to the 4th. Since these are the review problems, I'm not going to work them out, but I will just give you the answers so that you can check yourself. Or you might write this in the other form if you prefer, and it is what I prefer. Okay, and this form shows up when you're doing problems with terminal velocity, or you're doing problems in circuits. This shows up everywhere. Okay, let me know in the problem solving discussion if you have any questions about those. So where we left off is we were using initial conditions and boundary conditions to find particular solutions from general solutions for first order differential equations. And remember, first order means that the highest derivative present in the differential equation is the first derivative. Now we're going to talk about what happens when we need to find the particular solution for a second order differential equations. Well, it turns out when you solve for the general solution of a second order differential equation, instead of finding just one arbitrary constant, your solution has two arbitrary constants in it, which means we need two initial conditions or boundary conditions to be able to solve for those constants. Let's look at an example to see what that looks like. Okay, so here's a second order differential equation because the derivative is the second derivative. And the general solution of this one is, and again, we will get to the point where you can find this out for yourself, but there's a few other things we have to cover before we get there. Okay, so this general solution has two arbitrary constants, a and b. So we're going to do this with initial conditions first. If we have initial conditions, then we're talking about when time equals 0. Well, that's very common where we set our initial time. And we know, we're going to say that we know the value of y at time t equals 0. We're going to say that's 2. And then we're going to say that we know the first derivative of this function. So the first derivative evaluated at t equals 0. This notation gets pretty cumbersome. So a lot of times when we're working with differential equations, instead of writing dy dt, we'll write y prime. And when we want to say that y prime, our first derivative, is evaluated at t equals 0, we just write it like this. So that's how we're normally going to write our initial conditions. And we're going to say the value of the first derivative at this function is -1. So this will show up a lot if you're doing kinematics. For example, you would say, I know the position and the first derivative is the velocity. So if you know the initial position and the initial velocity, then you can solve for your two constants. Okay, so the first thing we need to do then is find out what the first derivative of this function is. So we're going to find the first derivative, and now I'm using the prime notation to save myself some writing. Let's plug in our initial conditions now. So we have y of 0, so we're going to plug 0 into this one. E to the 0, e to the 0, those both turn out to be 1s, so this function is just a plus b. Pretty simple. And that equals 2. And that's why it's really nice to set t equals 0. Well, it's nice if things work out that way because then your exponentials get very simple. They basically go away. Now we'll look at the first derivative evaluated at t equals 0. So then we have the same thing happen where our exponentials are going to turn into 1s. So now we just have a system of equations that we need to solve for a and b. 2 equations, 2 unknowns. So what I'm going to do is I'm going to multiply this top equation by 3, then write the second equation underneath it. And I trust you all remember how to do this, although it may have been a while since you did it, and you'll have to tell me. So when I add these together, we get 6a, the b's cancel out, and 6a equals 5. Alright, so now we solve for a is 5, 6. And we can use this equation, a plus b equals 2, to solve for b. So b equals 2 minus a. So 2 minus 5, 6 gives us 7, 6. So then our particular solution turns out to be 5, 6 times e to the 3t plus 7, 6 times e to the minus 3t. Now I'm going to give you a few to try yourself. Let me know if you have any questions about this. So I'm going to tell you what the differential equation is, I'm going to tell you the general solution, and I'm going to give you the initial conditions. And then you're going to solve for the particular solution. This one should look familiar. So I'm giving you the differential equation, its solution, the general solution, and the initial conditions. Here's your second one to try. This is omega, the Greek lowercase letter, but you know, it just looks like a W. And this shows up all the time as well, you know, when you're talking about oscillators. So this general solution, you see it has i's in the exponentials. Those i's are the imaginary number, the square root of minus 1. Just treat them like constants. So pause the video, take a few minutes, and find the particular solutions that go to these equations. Alright, so the first thing you need to do for the first one is find the first derivative. So that's x prime of t. X prime of t is minus gt plus a. Then we're going to plug in our initial conditions. So x of 0, well, when you plug that in, this term and this term both go to 0 because they have t's in them. So we're just left with b. And x of 0 equals 4. So this tells us that b equals 4. Well, that's easy. Then let's plug in our first derivative. When we plug in our 0, this term goes away. All we're left with is a. And we know the first derivative is 2, so it tells us a equals 2. This example is really easy. See, this is the case where you're given the position and the initial velocity. And since you recognize this as a kinematics equation, you probably could have solved this without going through the motions. But it's kind of nice to see it work out. So then we just plug in to get our particular solution. Alright, all done. That one's not bad at all. Okay, same procedure on the next one. The first thing we need to do is find the first derivative. And remember, I said to treat those i's as constants. So we're just bringing down a I omega. Okay, so we have our first derivative. Let's go ahead and plug in our initial conditions. So the value of the function at 0. This is one of those nice cases where our exponentials are going to just turn into 1s. E to the 0 is 1, e to the 0 is 1, so we're just left with a plus b. Nice. So a plus b, first, the value of the function at t equals 0 is 4. Next one, so now we're going to plug in our initial condition of the first derivative. So again, our exponentials are just turning into 1s, so we're just left with a I omega minus b I omega, and that equals 0. Well, that's nice, because if this is equal 0, we can just throw out the constants, and we can turn this equation into a minus b equals 0. So let's add this to the equation above it. A plus b equals 4. And of course you can solve these by substitution as well, whatever you like. So then we get 2a equals 4 and a equals 2. And we know from this equation a plus b equals 4, so 2 plus b equals 4, so b equals 2. Okay, a and b both equal 2. So if we write our particular solution, we just get 2e to the I omega t plus 2e to the minus I omega t. And of course, you can pull out the 2 and simplify if you prefer. Alright, so we've been looking at how we find the particular solution when we're given the initial conditions. Now let's look at the boundary conditions. So with initial conditions, we know the value of the function and its first derivative at an initial time. When we're talking about boundary conditions, we know the value of the function at 2 different points in space. So let's do an example. So let's say this is our function, y is a function of x, that's our general solution, and our boundary conditions are that we know the value of the function at x equals 0, and we know the value of the function at x equals 1. And we want to find a and b. So we just plug in our values for each boundary condition. So y of 0, we have the nice case where exponentials turn into 1s. For y of 1, we are not quite so lucky. And we have, well, that's a little bit of a mess. So we have a system of equations again, 2 equations, 2 unknowns. This time I'm going to solve using substitution. So I know a plus b equals 0, so I'm going to solve for a in terms of b. So I know that a equals minus b. Now I'm going to plug that in to this equation to get rid of a. So I have minus b e to the 3 plus b e to the minus 3 equals 3. Okay, let's solve for b. E to the minus 3 minus e cubed. This is not very pretty. I'm going to rearrange it to make it, well, different. I think it's a little bit nicer, but it's a matter of personal taste. I just multiplied through by e cubed everywhere. I like it better that way. And I know that a equals minus b, so I know that a equals minus that. So then we just substitute that back in up ahead, so a and b are both this lovely thing. So I'm going to pull that out front to save myself the effort of writing it again and again. So a is negative of that. And b is positive of that. Okay, there's our answer. A bit messy looking, but straightforward enough. Now I'll give you a few to try, and let me know if you have any questions about this in the problem solving discussion. So I'm going to give you the general solution and the boundary conditions, and I want you to find the particular solution. Alright, here's an oscillation example. Oscillations are everywhere in physics, so this is good practice. So your boundary conditions for the second one, y of 10 equals minus 258 e to the 20. Seems like a rather strange number to have for a boundary condition, but I just picked it so your math would turn out okay in the end. Alright, so pause the video and give it a go. Alright, let's plug in our values. So y of 0 is a cosine of 0 plus b sine of 0. So you need to know your unit circle. Cosine of 0 is 1, sine of 0 is 0, so this is just a. So this tells you that a equals minus 2. Hey, that's easy. Okay, let's do y of pi over 4. So we have a times the cosine of pi over 2 plus b times the sine of pi over 2. So I know that cosine of pi over 2 is 0, but sine of pi over 2 is 1. So this just gives us b. b equals 10. That's nice. That's why using this form to write oscillations is really nice, because it makes it easy to solve for your initial conditions. Well, it makes it easier for you to solve for your arbitrary constants. Let me know if you have any questions about that one. Alright, for this one, let's go ahead and get plugged in. Okay, well, a times 0 is 0. We keep our b. E to the 0 is 1. So we just have b. Y of 0 equals b equals 12. Another easy one. Oh, how nice. Okay, let's plug in y of 10. Well, that gives us 10 times a plus b times e to the 20. And we see that that equals minus 258 times e to the 20. And we just need to solve for a because we already know b. Well, the e to the 20s cancel out of both sides. So we have 10a plus 12, because we're plugging in our value for b. That equals minus 258. So we solve this for a, and we find that a equals minus 27. So our particular solution is minus 27x plus 12 times e to the 2x. Alright, great. So we've covered initial conditions and boundary conditions for first and second order differential equations now. Now we're going to go back and start talking about how we can actually solve for general solutions. The most basic type of differential equation that you can solve is called a separable equation. So when you have a separable differential equation, basically what you do is you rearrange what you have a little, and then you integrate. So I'll show you an example of what I mean, and I'm going to show you a really basic example. So this is one of the most basic differential equations you could get. And this one you can solve without even thinking about differential equations if you just know a little bit about calculus. But if you want to think about it in terms of differential equations, you just move the dx to the other side, and then you integrate both sides. So if you integrate dy, you would just get y plus, let's say our arbitrary constant is b. And over here you integrate this one, you get x cubed over 3. Now let's call our arbitrary constant c. Now when you're doing these, you actually only need one arbitrary constant. So you just pick a side and leave it there. And the reason is because b and c are both arbitrary constants. So basically you can combine them into one arbitrary constant. You could think of me saying c minus b. Well, that's just another arbitrary constant, and I'm just going to call it c. Let me know if that makes sense. Sometimes it bothers my students. Okay, let's do another example that's not quite so basic. This is the separable differential equation. So the first thing we need to do is rearrange so that we have all of our y parts on one side and all of our x parts on the other side. So the first thing I'm going to do is move the 6y squared x to the other side. And the reason I'm doing that is so that I can get to the point where I can use multiplication and division to get one thing on one side and one thing on the other side. So what we can do then is we can move, we want our dy to be on top and we want our dx to be on top. So we need our y squared to come to the bottom over here. And we need our dx to come up. So we're going to keep the 6 over here. And the 6 could go on either side. I'm just deciding I'd rather deal with a 6 than a 1/6. Okay, now we just need to integrate both sides. I'm going to rewrite this so that it's easier to see how to solve it. Now I'll rearrange this slightly. And when you're solving an equation that has a dy dx, that means you're solving for y of x. So we need to rearrange this so that it's a y of x. So I'm going to flip everything over. So I get y of x. So I'm flipping this, that means I need to flip this. So that is our general solution in this case. Let me know if you have any questions about this in the problem solving discussion. Now I'm going to give you a few to try. So I'm going to give you separable differential equations and I want you to find the general solution. I actually gave you the solution to this one last week, but now you can see for yourself why the solution is what it is. And remember, this is the equation for radioactive decay, so it should look familiar. So I want you to find the general solution for each one. So that means here you're looking for a solution of the form n of t. Here you're looking for a solution of the form x of t. And here you're looking for y as a function of x. Alright, pause the video, take a few minutes, and try these out for yourself. We want to put all the n's on the left side and all the t's on the right side. So that means we have dn over n equals minus lambda dt. And then we need to integrate both sides. So the integral of dn over n is log n, and the integral over here is minus lambda t plus c. And this is where a lot of my students in the past have gotten mixed up because it's been a while since they've had to do much with logs. So remember I told you last week to brush up on how logs work. So what this means is that n equals e to the minus lambda t plus c. Now I'm going to rearrange this a little. This is fine for your final answer, but it's not my favorite form and it doesn't look like what I gave you last week either. So if you remember how exponentials work, that means you can split it up like this. And now my last bit of funny business. E to an arbitrary constant is an arbitrary constant, so I'm going to rewrite e to the c as c. Yes, it's a different c than before, but they're all arbitrary constants, so I don't care. Alright, does that make sense to you? Let me know in the problem solving discussion. Any of these is correct, but this is my favorite form. And see, this is what we had last week. Okay, next one. This one is one of those that you can do with just basic integration, really. But we'll write it out formally. That's all. That one's pretty easy. Okay, last one. Let's rearrange this so we have all of our y parts on the left side and all of our x parts on the right side. So we have dy over e to the minus y on our left side, and 2x minus 4 times dx on our right side. We need to integrate. I'm going to rewrite this real quick. So this is actually e to the y times dy. And you can integrate the left and right side of different lines, but I just prefer to keep it all together. Okay, this is one of our easy integrals. And this is x squared minus 4x. Now things get a little funny again. So remember, we want to find y of x, and y of x is in our exponential. The way we can bring that down is by using a log. So we're going to take the log of both sides of the equation. So what that gives us is that then the y comes down. So we just have y as a function of x on the left side. And we have the log of x squared minus 4x plus c on your right side. And that's it. So one thing I want you to notice is when you're just integrating, you have a simple plus c that shows up on the end of all your equations. And that's why it's easy to forget about it and think it's silly, and it doesn't matter because you just have plus c getting added to every single one of your solutions. It doesn't work that way when you're doing differential equations. Your plus c on your integration line, yes, your plus c is just going to show up there. But depending on what's on the other side of your equation, it may be that your plus c is not going to end up just added on at the end. So in this one here, your c ends up next to an exponential. Here, your c is inside of a logarithm, and that's really important. This is not the same as a c on the outside of your equation. That's a different family of functions for your general solution. So don't just forget about your plus c's. They're important. that's where we're going to stop for today. We're going to take a break from differential equations now, and we're going to come back to them later at the end of the semester after we've learned a few other things. We have to review complex numbers because complex numbers are really important to solving differential equations. We have to learn about series, and series is where we're going to pick up next week. Alright, so leave me comments and feedback and questions in the problem solving discussion. I look forward to hearing from all of you.